For topic 1.11, we're going to talk about equivalent representations for polynomial and rational functions, kind of going back and forth, almost like a review day, but not all review, because we're also going to learn some new things. But let's recall that for a rational function, we have a polynomial on top and a polynomial on bottom. We've also learned that when that denominator is equal to 0, then the function has a vertical asymptote or a hole at that value. To go a step further, therefore we know, the three little dots mean therefore we know that the domain of any rational function is not all real numbers from infinity to infinity. We must remove the x values from any vertical asymptote or hole from the domain. So we are going to have many different intervals in the domain here for a rational function, because we know that at the holes and at the vertical asymptotes, we'd have to pick up our pencil and not include those values for x or those values for our domain. So in example 1, it says, let h of x equal to x squared minus 4 over x squared plus 7x plus 10. Write an equation for h of x in factored form. Factored form is the factored form with the factor showing, so we're going to have to make it all of the parentheses, and find any values of x where h of x has a hole or a vertical asymptote. Okay, so let's factor the numerator first. We know that the numerator is the difference of two squares, so it factors quickly to x minus 2, x plus 2. Fabulous. For that denominator, we would guess and check. This factors to x plus 5 and x plus 2. Hopefully your spidey senses are going off, because we know that we have this cancellation here of the x plus 2's, which means that we have a hole at x equal to negative 2. Additionally, we have a vertical asymptote at x equal to negative 5, because that's what's remaining here in my denominator, which still creates a vertical asymptote. Remember that the holes are what completely cancels, and the vertical asymptote is what doesn't completely cancel. For example 2, it's still using the same equation. It says find the domain of x from example 1. So typically, every function we're going to study in this class has a domain of negative infinity to infinity, meaning an entire number line can be used. However, we know that we have two places where this function would be undefined: at the hole, negative 2, and at the vertical asymptote, negative 5. So we want to talk about the number line that instead of saying everything on the number line, we have to go back and say everything except these two values that we found to be holes or vertical asymptotes. So this is negative 5 with a hole, and this is negative 2 with a hole. So once we pluck out those two values, the way we would write the domain for this particular rational function would be from negative infinity to negative 5, from negative 5 to negative 2, or from negative 2 to infinity. Notice again that all I did was take the negative infinity to infinity and create stopping points at negative 5 and negative 2, where the hole and the vertical asymptote is. So this has a vertical asymptote, and this is where our hole is. We had to pick those numbers particularly out of our domain, and then we can talk about the domain of the function. So our next question is going to kind of encompass almost everything we've talked about so far. Let's write an equation for k of x in factored form. So we're going to have to factor that whole thing. All right, I know that the numerator for k of x is going to factor to x plus 4, nope, x minus 4, sorry, x plus 3. I know that the denominator has a factor, GCF of x, so I'm going to factor that out first, and then be able to see that, oh, okay, I'm going to have the factors, if I keep going, first rewrite everything, x minus 4 on top, x plus 3 on top. We already factored out the x, and then we have x plus 5, x minus 4. There's the factored version of k of x. Now the first question, part B, says, what are the zeros of the function? Well, hopefully your spidey senses started tingling here, because we see that we have a factor that's going to cancel out. So the only zeros I have for this function are at x equal to -3. And since we canceled out those values, those factors x minus 4, that means that we have a hole in this graph at x equal to 4. Additionally, we still have vertical asymptotes at 2 places because after canceling, there's still 2 factors in my denominator that we can set equal to 0, which means my vertical asymptotes for this graph are going to appear at -5 and at 0. Ooh, we're good. There's so many things we can talk about with the rational function. What about the horizontal asymptotes? Asking you about horizontal asymptotes is really wanting to know first, is it Bobo, Botner, Betsy? Because this has degree 3 on the bottom, degree 3 on the top, it is bigger on bottom, which means my horizontal asymptote is y equal to 0. Notice that it switched to horizontal asymptote, so it's now a y equals equation as opposed to an x equals equation. Last but not least, before we graph it, we're going to find the domain. Well, we know that we have to pluck out the values that had a hole or a vertical asymptote. So if I were to draw a number line for this function, remember, a typical function goes from -infinity to infinity. But we have 3 places that are undefined. We have the value -5, we have the value -4, we have the value 0, where my graph has either a hole or a vertical asymptote. So we're going to have to go back, and instead of coloring in that entire number line, we have vertical asymptotes and holes at these 3 places. Which means to write the actual domain here, there's 4 sections, from -infinity to -5, from -5 to -4, from -4 to 0, and from 0 to infinity. Those are the 4 sections separated by a vertical asymptote here, a hole in the graph here, and a vertical asymptote there. So putting it all together and trying to pretty accurately graph this function, we have the following. First, we plot the zeros. Okay, well, we said the 0 is at -3. We plot the holes. We just hold on to the fact that at 4, 1, 2, 3, 4, we're going to have a hole in our graph. Hang on to that. We plot our vertical asymptotes. We have vertical asymptotes at 0, and at -5. Last but not least, we're going to add in our horizontal asymptote, which we found was y equal to 0. And I know it kind of like all puts it on the axes that we have, axi, but there's our boundaries for this graph. At this point, you can use your graphing calculator to help you sketch the final shape here, but we wanted to make sure we had the easy points plotted, your zeros, your vertical asymptotes, and remembering about your holes because that doesn't show up on your graphing calculator. Once we graph it, which please actually do this, it's going to look something like this. And it doesn't show up well on the graphing calculators because this is a very steep graph, but we know it's going to have to look something like this. I just make sure I go back at the very end and I add in that hole at 4. For this example here, when we write an equation in factored form for this function, we really just need to figure out what's happening at every point, every important point on this graph. So first thing I'm going to look for is my points of discontinuity, meaning my vertical asymptote and my hole. I know for this graph we have a vertical asymptote at x equal to 2, and we have a hole at x equal to 4. I also see that we have a horizontal asymptote at the value y equal to -1. Hopefully your spidey senses are tingling that if that is a number for my horizontal asymptote, that is a Betsy question. And since that Betsy question makes me know that the coefficients divided -1, I know that I'm going to have -1 over 1 as my coefficients for the top and the bottom. The last thing I see on here that's important is those zeros. We found the zeros to be where the graph crosses the x-axis, and that's at x equal to 3. If we put this all together, we know the following. We know that on the top, we have to have the factor that creates the 0 at 3. We also know that we have to have the factors that create the whole, which means there's going to be an x minus 4 on top and an x minus 4 on bottom. We also know that we need the factor that creates that vertical asymptote. The only thing that's left is making sure that your horizontal asymptote is taken care of. Again, because our horizontal asymptote is -1, that means the coefficients when I divide them would be -1 over 1. So I need to make sure I make the numerator or denominator, one of them, negative. Voila, we've written it in factored form. I want you to pause the video. I want you to try example 5 on your own, doing it exactly like that. Hopefully you did pause the video and actually try it. Here's what I see. I see that there is a vertical asymptote here and a hole here and a vertical asymptote here. So we have the following information. We have a vertical asymptote at x equal to 0 and at x equal to 3. We have a hole in the graph at the value x equal to 2. We have a horizontal asymptote on the x-axis, so that's at y equal to 0. And I see that it crosses the x-axis only once, meaning that it has a 0 at x equal to 1. Now, the horizontal asymptote meaning 0 means that this is a Bobo question. So it needs to make sure that at the end we have more factors on the bottom than we have on the top. So here we go. We would write g of x equal to x minus 1 takes care of the 0. X minus 2 on top and x minus 2 on bottom takes care of the whole. Then I need to take care of my vertical asymptotes. It would be x minus 0, which is just x, and x minus 3. There we go. There's g of x. As long as we have it bigger on bottom, we could add some coefficients in there, but bigger on bottom means that the horizontal asymptote is 0. Now we're going to take a little bit of a left turn here. If you remember back when we learned about Bobo, Botten, and Betsy, I talked about something called a slant asymptote. That occurs when the rational function is bigger on top by 1. We will have a slant asymptote. I also said that day that finding the slant asymptote is a problem for future us. Well, guess what? It's future us time. So if you look here, this function k of x is bigger on top by 1. The degree on the top is 3, the degree on the bottom is 2, so it's bigger on top by 1. It does have a hole at x equal to 2 because these would cancel out, but we still have a horizontal asymptote here. Notice that I have a whole equation this time for the horizontal asymptote, y equal to x plus 1. Previously, we just talked about what it would be parallel to, but today we're actually going to find the function or the equation for the slant asymptote. The best part about this is all it requires is long division. Long division of polynomials is exactly like long division of straight up plain numbers. So if you flip your page over, we're going to review how to do long division with numerical numbers and then apply that to polynomials just so you see it's the same thing. If I was doing numerical long division, if you remember, you set it up with 21 outside the little house and then 676 on the inside. You have your dividend and your divisors. 21 doesn't go into 6, so I skip to going over 67. 21 goes into 67 3 times. 3 times 21 is 63. We would subtract those terms, and we'd get 4. We bring down the 6, and we'd get 6, 46. We repeat. 21 goes into 46 2 times. 2 times 21 is 42. We subtract. 46 minus 42 is 4. So we would have a quotient of 32, a remainder of 4, and be able to answer this question as 32 plus 4 out of 21. Does that ring a bell? So the steps were divide, multiply, subtract, bring down, repeat. Divide, multiply, subtract, bring down, repeat. Okay, let's take those same steps and the same numbers and let's apply it to polynomial long division. I want you to notice that 676 divided by 21. 676 divided by 21. It's the same numbers, I've just applied it to a polynomial. If I do the same steps, I would put 2x plus 1, exactly where the 21 went, on the outside of the house as the divisor, and 6x squared plus 7x plus 6 on the inside as the dividend. Just like I did before, I skipped the first term and go to the second, and I would actually see how many times 3x plus 1 would go into 6x squared. I'm really only looking at these first terms. 6x squared divided by x squared is 3x. Then we multiply everything. 3x times 2x is 6x squared. 3x times 1 is 3x. Put everything in parentheses so that we can subtract the whole thing. That is so important to put it in parentheses. But subtracting is hard, so we're just going to add the opposites. I just changed all of the signs. The first terms can and should cancel. The next terms should subtract. 7x minus 3x is 4x. Then we bring down and we repeat. Notice again, I still got 4 and 6 as the numbers in polynomial long division. We repeat. 4x divided by 2x, just the first terms, is 2. And then I multiply. 2 times 2x is 4x. 2 times 1 is 2. Put the whole thing in parentheses and subtract. But subtracting is gross, so instead I'm going to add the opposites. The first terms can and should cancel. The next terms should subtract. 6 minus 2 is 4. So my quotient from the top of the box is 3x plus 2, and my remainder is 4. Meaning that my answer is 3x plus 2 plus 4 over what I was dividing by. So take a look at a second again. These are the exact same steps with the exact same numbers. One is just amped up to be polynomial long division. So let's use polynomial long division again to find the equation for the slant asymptote of h of x. Because by finding the answer to these questions, minus the remainders, don't care about that, we actually have the slant asymptote. So if I were doing this, we would say 2x plus 1 divided into 6x squared plus x plus 5. We ask ourselves, how many times does 2x go into 6x squared? 3x. We multiply. 3x times 2x plus 1 is 6x squared plus 3x. But we subtract everything. Ugh, subtracting is gross. We're going to just add the opposites instead. 6 and negative 6 cancel each other out. X plus negative 3x is negative 2x. We bring down the 5. We divide again. 2x and negative 2x, we would get negative 1. We multiply. Negative 1 times 2x is negative 2x. Negative 1 times 1 is negative 1. We subtract all of that, but subtracting is gross. We're just going to change the signs. Add the opposite. First terms can and should cancel. 5 plus 1 is 6. Now, I don't care about the remainder when it comes to the equation for the slant asymptote. So the remainder here, I know the answer to the long division question would be 3x minus 1 plus 6 over 2x plus 1. That's the answer to the long division question. But the slant asymptote is y equal to 3x minus 1. I don't care about remainders. So we do have to use a lot of our Algebra 2 skills to be able to find slant asymptotes. If you need more help on long division, when I come back, make sure that you ask for help on that. For example 7, it says let g of x equal to this rational function. Find the equation for any asymptotes of the graph of x. Okay, so first things first, let's just see if there are easy asymptotes here and that we can just find vertical asymptotes. But immediately I see that what? I see that it is bigger on top by 1. So that means we're going to have to do some long division. I don't want to do long division with degree 3 and degree 2 polynomials. I could. It would still work. It's just ugly. So instead, what we're going to do is we're going to factor g of x first and see if we can find any of the types of asymptotes it might have. So if we factor this, this is going to be x times x squared plus 4x minus 12 over x minus 6, nope, x plus 6, sorry, and x plus 1. The top is also going to factor again to x plus 6, x minus 2, all over x plus 6, x plus 1. Now hopefully your spidey senses are tingling. We have a hole right here, which is nice because then it's going to make my polynomial that I'm going to have to divide a lot smaller. Okay, being that I see there is still an equation, a factor in the denominator, that means I still have a vertical asymptote at x equal to -1. But because this is bigger on top by 1, I'm not going to have any horizontal asymptotes. Bigger on top by at all means that we have no horizontal asymptotes, but bigger on top by 1 means that we specifically have a slant asymptote. So our job is to find that slant asymptote. I'm going to re-multiply the numerator. X times x minus 2 is x squared minus 2x, so that I have one term to divide by the leftover term in the denominator after I take out the whole. And now I'm going to do long division. First step in long division is I ask myself, how do you divide x squared and x? Well, it'd be x. Then you multiply x times x plus 1 is x squared plus 1x. We would subtract all of that, but subtracting is gross, so we add the opposites. That means that we would end up with negative 3x plus nothing. There's still a bring down step here because our c was missing. We continue. Negative 3x divided by x is negative 3. That would mean this is negative 3x minus 3. Subtract, which means add the opposites. That means we have 3 as my remainder. Cool, great, whatever. I don't care about the remainder. I care about this right here. It tells me that the slant asymptote is the equation y equal to x minus 3. So here's all of the asymptotes for this graph. We have one vertical asymptote, no horizontal asymptotes, but we do have a slant asymptote. I could go a step further and ask you for the holes of this graph, which would just be at x equal to -6, but it didn't ask for that. Example 8 says, let d of x equal to 2x times x plus 4 times x minus 1 over x squared minus 2x plus 1. Which of the following about the graphs of d of x is correct? Now, if I just look at the answer choices, I see that it's asking me about the different type of asymptotes and holes it can have. So first thing first, let's eliminate it based on the end behavior. What's the degree of the numerator? It would end up being 3, and the degree of the denominator is 2. That's a bigger on top, specifically bigger on top by 1. So it will not have a horizontal asymptote. So A and B are gone since they talk about horizontal asymptotes, but it will have a slant asymptote. We now need to decide what type of holes or vertical asymptotes it may have. To do that, we need to factor the denominator. If we factor that denominator, it becomes x minus 1 times x minus 1. Okay, well, if I write my numerator back up here so we can see this, hopefully your spidey senses are tingling and you see that one of these is going to cancel out. So my brain is like, oh wait, that's a hole in the graph. However, if I actually rewrote this equation showing the denominator as a square term instead of as two separate factors, when I get rid of the hole, air quotes, in this graph, I'd only be getting rid of the power, meaning that that value at x equal to 1 is not a hole. It's actually a vertical asymptote. So the correct answer here is D. We have no holes in this graph because when I canceled it out, that value still appeared in the denominator here, which is my one vertical asymptote. Tricky, tricky. So yes, it needs to fully cancel. However, if that factor is still in the denominator, it's a vertical asymptote, not a hole. Example 9, sketch a picture of the rational function f of x with the following properties. The limit as x approaches infinity of f of x is negative infinity. Okay, so that's telling me that the right side should be going downward. And the limit as x approaches negative infinity, that's the left side. And since it's headed towards infinity, I know the left side should be going up. So there's my end behavior, meaning I don't have a horizontal asymptote here since my end behavior is one of the infinities. But it also tells me the limit as x approaches -1 from the negative side is negative infinity. So next to some sort of vertical asymptote on the left, we're going to be going down. And next to some vertical asymptote on the right side, we're going to be going down as well. Okay, if I were to sketch these things, I know that there is a vertical asymptote at -1. So here I'm going to draw it in. Pow, 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 pow. My vertical asymptote at -1. The other information I know from the limit statements is that as the graph goes to the right, the arrows should be facing downward. And as we go to the left, the arrow should be facing up. I know also that on the left side of this vertical asymptote, it should be going down. And on the right side of this vertical asymptote, it should be going down. So if I play connect the dots here, I know that I'm going to have some sort of part of this graph that goes like this. And then I have to also loop back around and follow the same rule. Taking another abrupt turn for this lesson, we're going to talk about polynomials again for a little bit. Go back to them and talk about what's called Pascal's triangle and the binomial theorem. Pascal's triangle you've probably seen before, but you may have never seen the binomial theorem. What these two things are going to allow us to do is expand expressions of the form a plus b to any power, because once we go past degree 3, it gets pretty tedious. And what I mean by that is, if we FOIL x plus 3 times x plus 3, we end up with x squared plus 6x plus 9. Not too bad, we can FOIL that real easy. But if I raise that degree power one more time, this becomes x plus 3 times x plus 3 squared, which is like x plus 3 times x plus x squared plus 6x plus 9, which I just factored. And then, whoa, I got to do all of that again. And so I distribute one more time, and it's triple distribution happening here. So it's x cubed plus 6x squared plus 9x plus 3x squared plus 18x plus 27. There's like, I mean, this is what I'm doing here. I'm doing this sort of distribution that looks like this. And like, this gets really tedious really fast. Imagine if this was degree 4 and I had to do all of these things so many times because I had degree 4 polynomial. We'd get annoyed real fast having to do this. What mathematicians realized by like year 1000 AD is that we can use something called the binomial theorem to expand any expression so that doing x plus 3 to the 7th power wouldn't take us like 4 sheets of paper. The binomial theorem is a very complicated looking theorem that I'm going to teach you a little shortcut for so that you don't have to deal with combinations and all of that stuff that you haven't really learned yet. These sort of things right here, n choose 1, n choose 2, n choose n minus 1, that's from like stats level or probability class. So we are not really getting into what all of that means, but I'm going to teach you how to use it. The n choose 0, n choose 1, n choose 2 actually goes exactly with Pascal's triangle, which I believe you've learned about before. Pascal's triangle tells us the coefficients to use in each row for the values of n choose 0, n choose 1, and n choose 2. So the value of n choose some number corresponds with the rth element of the nth row in Pascal's triangle. Please note that the first number in each row is the 0 element, not the first element. So if I were to ask you for the third element of the third row, you'd look at the third row and you'd find the 0, 1, 2, third term. It would be 1. What this allows me to do, and why the Pascal's triangle is super important, is because it can simplify the binomial theorem to the following. You are going to take the number from Pascal's triangle. You are going to multiply it times whatever is first in your binomial, a plus b, to the largest degree that you have and start making those numbers smaller. You're also going to multiply that by b to the 0 power and make it bigger. Once we do all of that, let's put a little cloud around this. This is important. Once we do that for each item in Pascal's triangle for that row, we will have expanded a polynomial. This is not going to make sense till we see an example. Please just hang on with me, okay? Again, just kind of re-emphasizing this. In Pascal's triangle above, we've circled the 5th row. Okay, easy way to remember that is these numbers, the second number in every row is what row it is. And we've circled the first 10. Well, that's the second element in the 5th row. 0, 1, 2. So if I said 5, choose 2, you'd say 10. Again, this is kind of talking about the formula that you don't need to know for how this came about, but if you're curious, it's called a combination of numbers and it utilizes the factorial. If you're interested, when I come back, you can ask me more about this. But what I need everyone else to be able to do is use Pascal's triangle and the binomial theorem to expand x plus 2 to the 5th power. If we had to do this by hand, most likely it would take us a whole sheet of paper. But instead, we're going to do the following. We're going to realize that a is equal to x and b is equal to 2, and that our degree power is 5. That means I'm looking at the 5th row of Pascal's triangle. I can't show you both at the same time, but it's already circled on your Pascal's triangle up there, so you should see it. If I was going to expand this, I would say we take Pascal's triangle number, which was 1, it's the 0 term. Then we have x to the biggest degree, and we have 2 to the smallest degree. So that's a and that's b. And I'm going to add the next number in Pascal's triangle, which is 5, times x to the smaller degree, so minus 1, and b to the bigger power, 1. I'm going to continue to make the x's smaller and the b's bigger, every time including a number from Pascal's triangle. You go all the way across Pascal's triangle, you should end up with an x to a 0 power when you've done your last bit. This is x squared and 2 to the 3rd. Pascal's triangle, x make it smaller, 2 make it bigger, and then 1, x make it smaller, b make it bigger. And then we just have to do a bunch of arithmetic, computation. If I do that computation and just simplifying each term, I get the following. Let me see if I can get it all on the screen at once. They're kind of big problems. Okay, sorry if that's a little small. We would have 1 times 2 to the 0. Well, 2 to the 0 power is 1, so that's just x to the 5th. 5 times 2, which is 10, x to the 4th. 10 times 4. Where am I getting the 4 from? Great question. 2 squared is 4. That's 40, x to the 3rd. 10 times 8 is 80, x to the 2nd. 5 times 16 is also 80. And then we have 1 times 2 to the 5th power, and 2 to the 5th power is 32. 32 times 1 is 32. And voila, in 2 rows, I have expanded that entire polynomial, instead of having to do that with like 8 sheets of paper. Let's try it again. We're going to use Pascal's triangle to expand 2x minus 1 to the 4th power. Okay, the first thing in my binomial is 2x. The second thing in my binomial is -1, and the degree or the row that I care about is row 4 in Pascal's triangle. So make sure you're looking at the correct row in Pascal's triangle. We begin with Pascal's triangle number 1. The x term, or the a term, which this time is 2x raised to the largest power, largest degree, 4. Notice I did put it in parentheses on purpose. You'll see why in a little bit. This is -1 to the smallest power. Pascal's triangle, a to the smaller, b to the bigger. Pascal's triangle, a to the smaller, b to the bigger. And you keep going until you've made it through the entire Pascal's triangle. Almost there. And then we just get to our arithmetic. I'm going to try to zoom out, and I know it makes it kind of small so that you can see all of it at once. When we do this, we have to hang on to a good number of numbers, because this is 1 times 16 times negative 1 to the 0, which is 1. So that is 16 x to the fourths plus 4 times 8 times negative 1, which is negative, I guess I should erase this and put a negative, which is negative 32x cubed, plus 6 times 4 times 1, which is 24x squared, 4 times 2 times negative 1, which is negative 8x. And then last but not least, we have 1 times 1 times 1, which is 1. Phew! We didn't have to actually expand all of that out to get the expansion for that binomial. Calming down a little bit, because that was a lot. Another way you can use the binomial theorem is to answer questions like this. What is the coefficient of the term containing x to the fourth when the expression x plus 5 to the 6 is expanded? So we know based on this that a is equal to x, b is equal to positive 5, and our largest degree is 6. That means we will be looking at the 6th row of Pascal's triangle. But we want to know the term containing x to the fourth power. So I know that my middle thing is going to be x to the fourth. So that means 5 would have to be raised to what power? 2. Every single time we do this, the power should add to 6. Okay, cool. All I need to know now is which term out of Pascal's triangle I want to use. Well, I want to use the fourth term. How do I know 4? The degree is 4. So let me go look at the degree 4, or the fourth term, sorry, in this Pascal's triangle. 0, 1, 2, 3, 4. We're going to use the number 15 in the front as my Pascal's triangle number here. So really what we're trying to do here is figure out what 15 times 25 is. Well, 15 times 25 is 375, so this would be 375x to the fourth. So to answer the question, the coefficient is 375. Pause the video now. I want you to try example 13. Now, hopefully a few things happened when you paused this video and you tried example 13. The first thing you noticed is that a is going to be equal to x, and b is going to be equal to negative 3, and my largest degree is going to be 8. So I need the 8th row of Pascal's triangle. Well, if you notice, I stopped giving you Pascal's triangle on row 7. But using your prior knowledge about Pascal's triangle, we can add another row here because you find more rows of Pascal's triangle by adding the diagonal numbers up, like this, and this, all the way around until you have your 8th row for Pascal's triangle. We want the third number in Pascal's triangle. 0, 1, 2, 3. We will use 56 here as my number from Pascal's triangle. So I have 56 coming from Pascal's triangle. I have x to the third power from here. And I have negative 3 raised to the 5th power. Why 5? 3 plus 5 is 8. Bleep, bloop, blop, you would throw all that into a calculator and figure out that this comes out to negative 13,608 x cubed, which means the answer to the question is negative 13,608. We've gone over a lot of things in this lesson, and it feels like it was all different pieces put together, and it kind of is, but this kind of puts a little bookend for us on our unit with polynomials and rational functions and kind of ties them both together with the use of slant asymptotes and the binomial theorem.